Um, in the first lecture was to derive the time-dependent Hartree-Fock equation. And what we did yesterday was, I mean, we did many things, but one thing was to take the linear version, so to linearize this equation. And when you, so what does it mean taking a linear, to linearize an equation? So perturb the density rho, you only keep the perturbation of the density to the first order. Okay, everything which is second order and etc. neglect. And you got, when you do that, you got RPA equation, so with which you can study vibrations, and essentially what it does, it builds vibration using particle Hall, coherent sum of particle Hall excitations. So you see, one thing is that, I mean, TDHF is more general than RPA. RPA is actually a reduction of TDHF where you only restrict to the linear limit, to the small amplitude limit. So you will only look at small vibrations. In principle, you can use TDHF to do larger amplitude. So you can do more general studies of vibration with TDHF. But still, will never be exact, because you have TDHF is an approximation. If you really want to have an exact prediction of what nature gives, you need to start from Schrodinger. So because TDHF has this limitation that you try to describe everything with a Slater determinant. So you remember? So keep in mind that it's really an approximation. So now maybe it's time to look at, we have looked at different applications of TDHF. So what I suggest is we look at, we go back to the theory and what did we use as an approximation and try to see what is missing. So if we want to go beyond TDHF, what do we need to incorporate? Because TDHF has is describing everything as independent particles, okay, moving in the mean field. Obviously, one thing you're missing is the possibility for nucleons to collide in a nucleus. Okay, so imagine you are a big nucleus. So I don't know how many, about titanium or nickel nucleus. We know about 50, 60 nucleons. So if I am a nucleon entering the nucleus, if I was living in the TDHF world, what I would just see is, let's get rid of my glasses, and what I see is just a blurry thing of students. Okay, I just see an average field of students, while in reality, so if I was to cross the nucleus, I will just cross and interact with just an average number of students. But now when I put my glasses on, what I see is each individual student, and if I try to go through the class, I will just collide with different people, and this collision between nucleons, between particles, is not accounted for in TDHF. So a nucleon will move freely in the mean field and without colliding with any nucleon. And when you think about it, it's crazy, because you have such a very dense system. The nucleus is very dense. You have nucleons, and they all are within 1-2 femtometers from their neighbor. And thinking of just going through the nucleus without colliding sounds stupid. Yet, the TDHF, this approximation, the mean field approximation, seems to work pretty well. So, do you have any idea why it's working? Why these collisions do not affect the physics of the nucleus? Why? Why are they transparent? If you collide them in the vacuum, they will strongly collide. They will have a hard core at half a femtometer or so on.
Yes, but that's the point. Here they are generated by all the others. So
yes, but that's an approximation. Why is this approximation working? That's my question. Exactly. The Pauli blocking is what saves us. So what happens is when you have two nucleons, say let's take one neutron, another neutron or proton, whatever, colliding with some energies. In the nucleus, they are essentially in their ground state, so they are all below the Fermi energy. Okay, so their energy here is below the Fermi energy. Now, when they collide, they change their energy. If they don't change their energy or their momentum, there is no collision, right? It's just going. They are transparent, as we say. So they change their energy. So one will go up in energy, one will go down. So you can have one which go up in energy in such a way that it goes above the Fermi level, which is fine because there is nobody here, so it can go above the Fermi level. But if you do that, the other one will go down in energy and will remain below the Fermi level, where you already have nucleons. And Pauli tells you you can't put two nucleons in the same state. Everything is already full. So when two nucleons cross each other in the nucleus, it just can't collide. There is no state available for this collision to actually happen. So they just go through each other without seeing each other.
So is this assuming there's an occupation of one orbital?
Yes, in the ground state, you will just occupy every orbital. So that's an... That's right. So essentially, we will go to this point when we put perine, for instance, we will have but essentially to a good approximation, everything is full until the Fermi level. It's only near the Fermi level that you can have some collision happening and scattering. But if you take two nucleons well below the Fermi level, the occupation number is 1. I mean, the state occupation is very close to 1. The collision is likely to be completely avoided. So, I mean, you can see that, for instance, when you shoot a neutron, a thermal neutron in a nucleus, you try to make them fission or whatever, and you want to look at the mean free path neutron. The mean free path of the neutron is actually quite long in the nucleus. It will actually be able to cross the entire. It's typically of the order of the size of the nucleus. So the neutron can cross the entire nucleus before it actually collides with something. You had a question? So it's but if they were in the vacuum and if they get close to another nucleon, then they will collide. But in the nucleus, because of this Pauli blocking, the collision disappears, and it's clearly a quantum effect. It's because you have Pauli exclusion principle. Otherwise, this will not work. So that's really the main reason why the mean field approximation, whether you are doing TDHF, RPA, Nielsen, shell model, whatever, you always often start with the mean field to start with, and that's why it's working. That's why you have shell effects. If there was no mean field, if the mean field was not working, there would be no shell effect. The collision will actually break the fact that you have magic numbers, for instance. So the fact that you see magic numbers, some nuclei with a number of nucleons which are more bound than the others, is clearly here because of this effect. If you didn't have this effect, the nucleons would move in a chaotic motion. They will not remain in their levels, and then the magicity will not be manifest itself. Okay, so you really have the Pauli blocking is really the main explanation why it's working. Okay, so you can, to a good approximation, as long as you remain to low energy, you can neglect these collisions and describe everything at the mean field level. Now, what do you neglect again? So again, TDHF is not exact. So even if you neglect the collisions, if you can neglect the collisions, there are other things which could play a role and which you neglect when you are describing everything with one Slater determinant. So what sort of correlation do you neglect? Have any idea? So one thing you would neglect is pairing. Okay. So what is pairing? Pairing is essentially when you have two wave functions with a strong spatial overlap. They will spend a lot of time together. If the nuclear attraction, the short-range nuclear attraction is attractive, then they will actually try to form a Cooper pair. So they form a pair, they try to move together. So nucleons like to be paired, it's like you have two nucleons which will move in the nucleus together in a very, very naive picture. In practice, what happens is when they have a strong overlap of their wave function. So usually it happens for time reversed states, and you can see why. If you have a nucleon with spin up turning that way, the time reversed state is spin down turning that way. So the spatial wave function is the same. Okay, they occupy the same region of space. So they spend a lot of time together. So they interact more than with other nucleons which are somewhere else in the nucleus. So this pairing, if you have an independent particle picture, you won't have this possibility to have two nucleons moving together. So we'll talk about pairing, how we incorporate pairing. We know it's important. We know it has to be here for different manifestation. Another thing which we are missing in TDHF, which I discussed yesterday, you remember? Tunneling, yes. The tunneling of the Mandy-Body wave function you will not have, because you force the system to be only in one Slater. But if you want to fuse two nuclei by tunneling, then you either fuse or you separate with a probability between 0 and 1. And for that, you need at least two Slaters. So in general, configurations which requires more than one Slater, so tunneling is one of them, but you can also have reactions where the nuclei can either transfer, I don't know, 10 nucleons or 1 nucleons, and that should lead to different Slaters at the end. This sort of configurations neglected in TDHF. You force everything to be in one Slater, so that's an approximation. Now let's go back to the pairing now. What are the manifestations of pairing in nuclei? Higher binding energy of what? Yeah, so the nuclei with an even number of nucleons, even number of protons and even number of neutrons are more bound than those with an odd number, okay? Because one nucleon will be unpaired, and then you have... so the pairing energy clearly brings down a little bit the energy, so that's one manifestation. What else? Sorry, staggering, so that's what we were talking about, the staggering, so that odd-even mass staggering. An odd nucleus has less bound than an even mass nucleus. Another manifestation? The fact that the ground state are in 0 plus, indeed, for even nuclei, yeah. Neutron capture cross sections. I haven't thought of this one. Why it will be affected by pairing? You were saying something? Yes, excited level. So if you start from an even nucleus, usually the first single particle level you can populate will be at about 2 MeV. So you need to break a pair and that costs about 2 MeV. While for odd nucleus, the nucleon which is alone can move to whatever energy you want, actually. Okay, so there is an effect of neutron pairing on neutron capture. I haven't thought of that. That's a good point. Yes, that's correct. So we will see an example of that. So that's how we actually treat the pairing. Something else? Maria, you are not allowed to give an answer. Rotation. The moment of inertia is the one of not the one of a rigid body. So when you have a nucleus rotating, essentially it has a superfluid phase. So the pairing induces a superfluidity, and this superfluid phase doesn't contribute to the moment of inertia. Then when you try to rotate faster and faster and faster, at some point you bring enough energy for the a pair to break, and suddenly the moment of inertia come back to something which is closer to a rigid body. So that's another manifestation of pairing. There is another one when you collide two nuclei, and they are superfluid, so they have pairing. When you collide two nuclei, they can transfer nucleons. If you don't have pairing, typically the probability to transfer nucleons, if the probability is small, the probability to transfer two nucleons will be the product of the probability to transfer one nucleon. Okay, so it's an independent process. But if you have pairing, they can be transferred as a pair. So it's a correlated pair transfer. It's quite a complicated subject, and it's not clear how it works exactly, but essentially pairing will favor the transfer of two particles. So in order to describe all that, you need to find a way to go beyond TDHF and incorporate pairing. So we will look at that for this first lecture today, before the break. So if I want to describe a state which in principle have pairing in it, it means that my wave function in principle, so like the exact one, the exact wave function which will have pairing, will be a superposition of a Slater determinant. So you understand what I draw here? It's actually a mean field, and that's the nucleons occupying below the Fermi level. Okay, and I call that a quantum state. So that would be my Hartree-Fock ground state, if you want. And from that, if I want to build pairs, if I want to have pairs moving together, what I will do is to have states which are two particle, two hole excitation on top of this mean field. So I will take two particles, remove them from the Fermi C, that makes two holes, and I put them above, that makes two particles. So I move them together, that's a pair. Okay? So you will have two particle, two hole. Okay, so that's how this sort of state where you scatter a pair of particles across the Fermi level is how the pairing will manifest itself in a quantum state. Now, we already have an idea of what the strength of the pairing energy is. It's about 2 MeV. We said we need 2 MeV to break a pair. Essentially, the pairing residual interaction, so the interaction which goes beyond the mean field, will be able to move a pair like that by about 2 MeV. So you see that the nucleons which are well bound, which are deeply bound, they can't be paired. Because if they were paired, you move them by 2 MeV, you end up in a state which is already occupied. So by Pauli blocking, you can't have that. So it's the same argument as for the collisions. So that's why pairing only affects nucleons which are close to the Fermi level. Superfluidity comes only from these nucleons. So it's a relatively small effect. You know, it's only maybe 10% of the nucleons in the nucleus which will have, at maximum, will be superfluid. So you don't have an entire nucleus to be superfluid. It's only part of it, and it's the least bound nucleons because of Pauli again. And for the same reason, magic nuclei or doubly magic nuclei don't have pairing. And you can see why, because the pairing gap, the magic gap is usually more than 2 MeV. So the pairing is not strong enough to scatter a pair by across the magic gap. Therefore, the pairing doesn't manifest itself in doubly magic nuclei because of quantum Pauli blocking. Okay, so ideally we would like to do that, but if we do that, the problem is we will have, in addition to our usual one-body density matrix, which are a value of A dagger alpha A beta. So that's, you remember, the matrix element of the one-body density matrix. And that's all we need to describe TDHF. You know, TDHF is just describing the evolution of this object. So that's fine for this Hartree-Fock state. The problem is now, if I want to describe pairs moving like that, what I need, in addition to that, I will need an expectation value of A dagger alpha, A dagger beta, A gamma, A delta. I will need matrix elements which are more complicated, where you have you make two holes and you make two pairs, two particles, two hole states. This will be matrix element of the two-body density matrix. Okay, that's a one-body density matrix, and that's a two-body density matrix. Now that's a big job to incorporate that, to make a theory which will solve properly the dynamics of the two-body density matrix. So, well, the idea will be to make an approximation of that. So now, before I tell you how we incorporate pairing, what approximation we do to incorporate pairing in an approximated way, let me go back a little bit and try to give you an idea of how we incorporated correlations at the mean field level. So I had some questions after the first lecture which were very relevant. The question was, so you are trying to describe a nucleus, which obviously is a correlated object, like all the nucleons are together in some region of space. Okay, if one nucleon is found somewhere, then the other nucleons are nearby and not on the other side of the room. So it's a correlated object. That's our definition of a correlated state. But we described everything with an independent particle state. And something sounds wrong when you do that, okay? So, and the trick here, you may not have realized, but the trick was that we break symmetries. The symmetry of the exact Hamiltonian are not the same of the symmetry of the mean field. And that's how we were able to describe a nucleus located somewhere in space. So what is the first symmetry we need to break in order to have a nucleon sitting somewhere? Sorry, a nucleus sitting somewhere. Translation, invariance under translation. So in principle, the exact Hamiltonian is invariant under translation. The interaction between two particles here or between two particles here is the same. Okay, it just depends on the distance, not on where they are in the room. But what we did at the mean field level, if we impose to have invariance under translation, because H depends on rho, so if H was invariant under translation, it would just be a flat potential. If it's flat, the nucleons are going everywhere. They are not correlated. Okay, they are not going to be localized somewhere. So in order to have a potential which localizes the nucleon somewhere in space, we needed to break this invariance under translation. That's how we incorporate correlations at the mean field level, is by breaking symmetries of the exact Hamiltonian. So do you have can you give me another example of symmetry we can break in order to incorporate more correlations at the mean field level, so still at Hartree-Fock level? Yeah, rotational invariance. If you break rotational invariance, you allow a particular direction for your mean field, so you can deform it. If your mean field is deformed, your density is deformed, so you are describing a deformed nucleus. Okay? If you force your mean field here to be rotational invariant, you will only be able to have a spherical mean field, and therefore you won't be able to describe properly deformed nuclei. Okay, so we break rotational invariance, we break translational invariance. We can do that with different symmetries. Now it's a bit more tricky for the pairing. What symmetry are we going to break in order to incorporate pairing? Sorry? No, not time reversal. Time reversal, yeah, no, we don't break time reversal. We will break time reversal to describe odd nuclei, because they are not time. Wave function is not time reversal symmetric. In TDHF, by the way, the Hamiltonian is not time reversal invariant. If it was time reversal invariant, it will not move. So in order to allow the system to move and to have currents which are time-out quantities, you need to have an Hamiltonian which breaks time reversal symmetry. But that's another one for pairing. What is the one for pairing? I'll give you a hint. The way we are going to approximate that so we approximate this expectation value of A dagger, AA by the product of two expectation value, one of A dagger, and one of AA. If I have a Slater determinant, what will be this matrix element, this object? 0. Why? Yeah. So the state has a good number of particles. So if on the right you have, say, A particles, you create two particles that give you A plus 2 particles. On the left, you overlap with a state which has A particles. Of course, that's going to be 0. Okay? An overlap of a state with A particle with a state with A plus 2 particle is 0. They are not part of the same Hilbert space. Yes, we break the conservation of the number of particles in order to incorporate the pairing. So that's the idea. And then when we do that, we will have these objects to treat, which are called the anomalous density. One body density or anomalous density. And this one will be K star alpha beta, and this one will be, sorry, not K, kappa delta gamma. So in order to, so just to repeat a little bit, we want to incorporate an approximation of these two-body two particle to hole correlations. And we do that by approximating the two-body density matrix as simple product of expectation value of A dagger, and AA. That's encoded in what we call the anomalous density. In order to have this quantity to be non-zero, the state doesn't have the good number of particles. So it will be, the state will be a superposition of n particles, n plus 2, n minus 2, n plus 4, n minus 4, etc. And in doing that, we will be able to describe this anomalous density, which we use to describe pairing in some approximated way. So these objects are not very complicated, much more simpler than the initial one. And what people do is to generalize the one-body density in order to incorporate these kappa and kappa star. So the generalized one-body density is usually written R, and it's a matrix which has rho and kappa. And you see, if you do that, you just have a you have two columns, only one line, so you need to add another line if you want to have a square matrix. And kappa is anti-emission, so you will have kappa star with a minus sign. And here you will so that's your generalized one-body density. It's a little bit more complicated than what you have in TDHF. In TDHF, you just have that. Now you have a more generalized object, more complicated object. But that's a price to pay in order to incorporate pairing. So the pairing will be encoded in these objects. Okay? If this is 0, you have no pairing. That's a pairing correlation are approximated by the kappa and kappa star. All right. So what do you think the generalized version of the TDHF equation is going to look like? Sorry? Yeah, it will be the same equation with a generalized Hamiltonian. So I'm not going to derive it. It's not very complicated, but that's relatively standard. But essentially, to give you the flavor of what you get is an equation which we call the time-dependent Hartree-Fock-Bogoliubov equation. Wheel equation again. And now we have a generalized Hamiltonian. So instead of having an Hamiltonian which just depend on rho, we have an Hamiltonian which depend on rho, kappa, and kappa star. And what's the form of this Hamiltonian? Well, obviously it will have the Hartree-Fock single particle Hamiltonian in it. But it will have also a pairing field, so something which will act principally on this kappa. And well, I need to check. I never know what which one has stars and so on. Minus delta star and minus H star here. It's essentially some sort of convention, but which is useful if you want to know the sign and the star. You want your density, for instance, to be Hermitian. That's the sort of thing you want to preserve, hermiticity and so on, and that's why you end up with a form like that. All right, so how do you get the delta? Well, remember that the H was obtained by taking functional derivative of a energy density functional with respect to rho. So now, if you want to incorporate pairing, you have a more complicated energy density functional. which does not depend only on rho. It will depend on rho, kappa, and kappa star. Well, we usually write kappa and kappa star, but at the end of the day, it's just the same thing. I mean, it's just complex conjugated of each other. And for the delta, well, that will be the functional derivative with respect to kappa. Now I need to check again. Yeah. Notice the order of this index here. So you have alpha beta here, then you have beta alpha, but for the pairing field, they're on the same order, alpha beta alpha beta. Okay, so it's again, I didn't derive the TDHF equation. I just wanted to give you the flavor of what we need to do in order to incorporate the pairing and what you end up with in terms of an equation. It's not necessarily much more complicated to solve than, in principle, than Hartree-Fock, but the space is obviously larger, like the matrix is larger. In addition, in TDHF, you need to look at the occupied part of rho. Now you will need to look at the occupied and unoccupied part. So the space is much bigger. But the form of the equation is really the same. So the algorithm will be the same, for instance. The algorithm we discussed yesterday, or yesterday for TDHF, will be the same for TDHFB. Okay? Okay, so let me finish this before break. So I told you how we incorporate the pairing at the level of the density itself, the generalized one-body density. Now, what the state look like, that's what we are going to discuss now. When I wrote the state here, that's an exact state, a state which will incorporate pairing correlation exactly. This is a Slater determinant, this is a Slater determinant, but we are just having a sum of Slater determinant. So it's beyond TDH, it's beyond Hartree-Fock. And okay, so let's see how we can actually, what we need also is something which now breaks the number of particles. Here we see that this state will have an exact number of particles. You see, if you have, that's a Slater determinant, it has n particles. Here I still have n particles. I make two holes, but I create two pairs. So the idea of actually the state now which will break the number of particles, which is the we have in Bogoliubov, in Hartree-Fock Bogoliubov, will be to approximate that by, by say something like C2p. So 2p is when I put two particles on top. So I add two particles and state where I actually remove two particles. So you see now I have n plus 2 particles here, n minus 2 particles here. Okay, so that's the idea what the state will look like. So let's write it in a more formal way. So what you have is psi will be so the Hartree-Fock ground state. Oh, sorry. No. You will have a state which has a superposition of 0 particles, 2 particles, 4 particles, 6 particles, etc. So you will have state where you have 0 particle plus state where you have just two particles. So you create two particles on the vacuum, plus states where you have four particles. So you create two pairs, case, A dagger alpha, A dagger beta, C gamma delta. Okay, so 0 particle, 2 particle, 4 particle, 6 particle, etc., etc., etc. Now you can rearrange that a little bit. You can probably easily see that if you were to, you could write that as a product. Oh, I should use alpha beta. Of an object which will have just something without operators. So say K. What did I use here? K alpha beta plus Q alpha beta. I'm just changing the letters because it's not the same coefficients. It's not exactly the letters I used in the notes, but that's the same idea. So you will have a product of this object where you have a constant plus something proportional to two creators. So you see, for instance, when you develop this product, say when you take only the case, the product of the case, okay, so you will have many Ks acting on the vacuum. There is no creator at all, so that will be this term. Now if you change one of the Ks by one of the Q, so you have product of all the Ks and one of them, for one of these bracket, you just take the Q and the A dagger, then you are creating a pair. So that will be this state. Okay? Now if you take K, Q, Q, you will have created two pairs. So something like that. So you see that we can write formally something which is a sum of state with 0 particle, 2 particle, 4 particle, etc., to something which is a product of a constant plus A dagger acting on the vacuum. So that's one thing. Now we can go one step further. Why do I want to have different number of particles? In principle, I'm describing a state with n particles. But if I stick to a state which has exactly n particles, I won't be able to have pairing. So you would like only n plus 2 and n minus 2? Yep, that would, I mean, if we were able to describe the pairing properly with only n plus 2 and n minus 2 states, that will be good. But unfortunately, you need to have the superposition of 0, 2, 4, etc. particles. So your state at the end doesn't look like something which has a right. I mean, it's not describing a nucleus, for instance, with a given number of particles. But what you will do is to force to have the average number of particles correct. So when you have a distribution like that, which has obviously a probability to have 0 particle, 2 particles, 4 particles, etc., you will have, if you were to plot this distribution, distribution. You will have a distribution like that. And what you can do is to make sure the average here is the one corresponding to the nucleus you are trying to describe. But if you want to have pairing correlations with this approximation, you have no choice but taking into account all possible combination, 0 particle, 2 particle, 4 particle, etc. Even if 0 particles, 2 particles have a probability which at the end is almost 0, they have to be there in the way you write your state. Yeah, yeah. We are trying to build this. Sorry. Yes. So that will be if you want. This will connect a state with 4 particles with a state with 2 particles. This one will do the opposite. Will connect. A state with 2 particles with a state with 4 particles. Okay. So you need these two. One will just. If you don't have these two, anyway, you won't be able to describe a density which is Hermitian, and you need something Hermitian. Your generalized density has to be Hermitian. So if you have K star, you need to have also K. Otherwise, you can't build something which is Hermitian. Okay, so the reason why I'm trying to rearrange that a little bit differently is because I want to end up with something which looks like something we already know. So if you remember, for Slater, we have a product of A creators acting on the vacuum. In second quantization, that's how I will write a Slater. So I have A dagger 1, A dagger 2, A dagger, etc., up till A dagger A. So I create A particles. That's for one set. Now what I'm trying to do is to write my psi here as something which is also, which has the same mathematical structure. Okay, which is a product of some operators acting on the vacuum, on a vacuum. And if I can do that, then I know I will be able to use the same mathematical tool as I used to solve Hartree-Fock. I will just have something a bit more complicated, but that will still be a generalization of the Hartree-Fock case. So something which is a product of operators acting on some vacuum. On the vacuum. Now I'm trying, again, you see, if I can write psi like that, I really have something which is which has the same mathematical structure. When I do that, I have independent particles. When I will do that, I will have independent quasi-particles. So it's just something a bit more generalized. So let's go back to this expression, and what I can rewrite that as something a bit differently, with which will be a product of objects which have A's and A dagger. And in particular, do we have some inside the bracket? Yeah. Let me just check if I did it correctly. So again, I changed my object. Here I was using K and Q. Now I use different letters. That's just a convention. I use U's and V's, which are complex numbers. Now, I didn't show you how we get from here to here. What I will do in a minute is to show you how we go from here to here in a slightly simple version, which is the BCS approximation. So BCS stands for Bardeen-Cooper-Schrieffer. That was the guys who actually described superconductivity with Cooper pairs. In the BCS approximation, you have an object which is a bit simpler. Essentially, the U's and the V's, they only connect states which are time-reversed symmetric. So your U ij will be actually ui delta j I bar. So I bar stands for the time reverse symmetric of I. For instance, if I stands for if you have spherical symmetry, you can have a state described by J and M, the usual angular momentum J and its projection M. The time reversal symmetric I bar will be J and minus M. Okay, so that's the time reversal symmetric. So BCS is just making the approximation that these U's and V's are only coupling states which are time reversal symmetric. So in particular in this case, this state a product over I of ui plus vi. Now I need to check again. So uai minus vi a dagger I bar. So that's creating a particle in the time reverse state and annihilating a particle in the initial state. Now you also need to do the same thing for creation of the particle in the state I and annihilation in the time reversed state. And here the coefficients will be U's and V's. So that's how you will write your BCS state. All right? And now you just expand. So this term times this term will give you, and this is acting on the vacuum. Now you see that when you have this times this, you have an annihilator acting on the vacuum. That's gonna kill. Okay, it's not going to contribute. The same is for this times this. It's gonna kill the vacuum. So you need to have this times this, and this times this. So you have ui vi a dagger I minus vi squared a dagger I bar a dagger I. Yes. So now for this you just use the the anti-commutation relationship for operator. So you can write that as 1 minus a dagger I, AI. Okay? But if you have the AI, it's an annihilator. Acting on the vacuum, it's going to give 0. So this is just not contributing. So at the end, what you get is psi, which is product over I of, so you can factorize the VI, and what you have is minus VI squared. Did I do something wrong? Should it be a plus? It should be a plus, right? It's a plus here. Plus VI squared, a dagger I, a dagger I bar. Yep, thank you. Correct. I, a dagger I bar. Really? You have a minus. Oh, yeah, okay. It's a plus, yeah. So it's a minus. And let's keep it a minus. Oh, yeah, it becomes a plus when you swap I and I bar. So it doesn't matter. Anyway, it's just the form I want to reach. I'm sure I did it properly in the notes. So you see, what you get is something which indeed is like this form. Okay, so I just showed at the BCS level how this is equivalent to that. Now, let's go. So that means that this is a possible way to write a state which will be a superposition of different number of pairs, and this is what we call our beta alpha, which I wrote here. Okay, so that's a quasi-particle annihilator. So what you see is that your state is actually now, so whether you are at Bogoliubov or at the BCS level, your state is a product quasi-particle annihilator on the particle vacuum. And in particular, you see that if you actually try of this quasi-particle annihilator on psi, what do you get? Now, I forgot to mention that you can write the U's and the V's in such a way that the beta will obey the anti-commutation relationship for fermions. Okay, you choose the U's and the V's in such a way that, for instance, beta, alpha, beta, gamma, anti-commutator is equal to 0. So that means if you do that, that means if you try to apply twice the same operator, that gives 0. Okay? So if you try to kill a quasi-particle where you have already killed it before, then you are going to get 0. It's like if you try to kill twice the same particle in the same state. Because you can't put two in the same state, then at the end you end up with 0. This is why we call that a quasi-particle vacuum. Because if I try to kill a quasi-particle on this state, I get 0. So it's a quasi-particle vacuum. Now I can create as many quasi-particle I want on this state. For instance, I can create and that will be a 3 quasi-particle state. And you see they are independent because they have exactly the same structure as what you have for independent particles, for slaters. So BCS or Hartree-Fock-Bogoliubov is just generalization from independent particle to independent quasi-particles. All right, we should probably have a break now. And after that, I will show you a quick movie where we actually play with this at the BCS level, and you see the V's which tell you the probability for your pair to be occupied, how they can move in time, and so on. Wrap up. These movies were not done at the TDHF level. They were done with, I mean, the one for fission were done at TDHF plus BCS. So with a state like that. So this state essentially tells you that for the single particle I and its time reversed I bar, its occupation number for these nucleons is V. So V is just telling you how many, what is the occupation number of this single particle state, okay? And you need that to do fission. I'll show you why in a minute. So if you solve these systems using BCS, so with a state like that, you see the nuclei fission nicely. And what you do, but you can't start from the ground state. So if you were starting from the ground state, so whatever nucleus it was, fermium 258, I guess, that's a ground state. And you have a fission barrier, and then it can eventually fission. So if you start here, well, it's not going to fission because there is no tunneling. And BCS is not helping for that. BCS or Bogoliubov, so the pairing is not going to help you tunnel. It's a different sort of correlations you need. So you need to go away. So you need to stretch your nucleus. And you stretch it, and you start somewhere here, or here, where the arrows are shown. And then you let it evolve with TDHF plus BCS correlations, with pairing, and then it eventually fission. Now, I mean, you can start earlier, it just takes longer computational time, but you need to start after the barrier. Now, first, how do we get a potential like that? We get a potential by minimizing the energy, solving static Hartree-Fock, so no time dependence. And we just force the system to have some deformation, quadruple deformation, octuple deformation, whatever. So we minimize the energy under a constraint that the system should have some deformation which we fix. So it's an external potential which forces the system to have some deformation. And you do that for many points, and then you get some values which fixes what is the potential energy. Okay, now why do we need BCS to have the system evolve in time? I'll show you one thing. It's a movie where you start with this configuration here. If I do it with TDHF without pairing, the system is not going to fission. It's going to stay here. It's not going to fall the potential energy. If I do it with BCS, it's going to fall here. So that's what you will see here. It's so that's the density that we had before. And the interesting plot is this one. What you see here is the V. This V here. And I tell you, it tells you how much the state is occupied, how much the pair is occupied. So, and that's a single particle energy. So, for instance, when you have minus 15 MeV, so your single particle is well bound, its occupation number is 1. And if its occupation number is 1, it means that you will be able to rewrite the state. If you had only occupation number 1 or 0, you will be able to write the state as a Slater. And in this case, there is no pairing. So that's why the nucleons which are well bound, they are not paired. They have no pairing. We already discussed that because of Pauli. However, when you get close to the Fermi surface, so the Fermi surface is at minus 5 MeV, minus 6 MeV here, then you have occupation number which are between 0 and 1. So that's where pairing is acting on the nucleus by distributing these V's between 0 and 1 around the Fermi surface only. Now, if you assume this occupation number to be constant and not evolve in time, that's what we will call frozen occupied approximation, whatever, some jargon, then the system will not fission. But if you let them evolve in time, it will fission. And I'll show you what happens when the system starts fissioning. You see all these occupation number rearrange themselves to some new numbers. If you don't let these numbers move in time, the system will not fission. So it's only recently that it's not my calculation, but we in the community managed to put pairing in a time-dependent fashion in such a way that you can study things like fission. Yes, it is. Here is the neutrons we are looking at. Sorry, I should have mentioned that. At the end, these are two tin nuclei, so they are magic in protons. So if you were plotting that for protons, you will have 0. You will have 1 and zeros. All right, so now, do you have any idea why I need the time dependence of this object for the system to fission? It's not very complicated, but okay, now so I show you one of these. You recognize this plot? How is it called? Nielsen diagrams. So essentially what it shows is single particle energies versus the deformation. So if you have, for instance, your nucleus and at a spherical point, you will feel everything and stop where you have you have fully you have put all your states. Now what happens if you say you have a nucleus, I don't know how many nucleons you put to get here, maybe it's fermium, something like that, and then you stretch the nucleus. You see the energy goes up. Then there is a crossing of particles. Then your Fermi energy goes to the other state. Then you have another crossing, goes down, goes up, goes down, etc., etc., etc. All these bumps here are what forms the fission barrier. So if you were looking here it's relatively smooth, but if you were plotting in a finer graining, you will see some structure like that, which are due to this single particle crossing. So you could actually plot something like that just based on Nielsen. Okay, so when you do archifoc and you minimize your energy for a given deformation, you will have occupied all the state up to some level here. Then you do that for another deformation. If a crossing occurred, this state which was initially occupied will become unoccupied, and then you will occupy another one because of crossings. Does that make sense? Now, if you do TDHF and you fix the occupation number to be 0 or 1, or even if you do BCS and you fix this occupation number to not evolve in time, what will happen? Say you start here, okay, or here maybe, and you let your nucleus evolve. Well, it will try to evolve, but at this crossing here, it will not go down because it will not rearrange the occupation number. So it will keep going up, going up, going up, going up, and it will not fission. So when you don't allow a time-dependent reorganization of the occupation numbers, so the time-dependent pairing effect, your system can get stuck in some local potential energy, while pairing will help the system to fission. So that's an example of, even if pairing is a tiny effect, I mean, it's basically 2 MeV, few MeV of binding energy with respect to total binding energy, which is huge, like 8 MeV per nucleon. Okay, so the pairing is just a correction, but it's a correction which can have a dramatic effect in the sense that you need it for fission to occur, for instance. Okay? Yeah, okay. So, how am I going with time? Yes, or Artifok-Bogoliubov is you end up with a state which does not have a good number of particles. And it's always a bit, I mean, it's a bit of a problem. People don't really like to calculate observable. Well, they want to calculate, for instance, some observable for calcium 44, for instance. But what they actually calculate will be a bit of calcium 44, calcium 46, calcium 48. So it's always a bit tricky. So you have techniques to project your Hartree-Fock-Bogoliubov or your BCS state in a state which has the right number of particles. I give that in the note. You can look at it. It's relatively straightforward. But the problem is when you do that, you go out of the variational space you had at the beginning. So when you project, say you want to extract the component which has the right number of particles in your state, you end up not with an independent quasi-particle, but a sum of independent quasi-particle state. So it's outside the variational space you had at the beginning. So it's not sure your calculation will be optimized for that. So it's always a bit, you always need to be careful what you are calculating with these theories. If you are calculating something which is outside the variational space you started with, your theory is not necessarily optimized for these observables you are looking at. That's in a nutshell a few pages in the notes. Now what I would like to quickly address is a different variational principle. I won't do any derivation, but I just want to give you the feeling that there are different variational principles, and each of them will tell you something different about your theory. Will tell you something different about what you can and what you can't do, just by telling you, okay, what is the variational space you have used. So if you remember how we got TDHF, we started with a specific Dirac action, which was a function of the state psi and its Hermitian conjugate psi star. Now we have other possibilities for variational principle. So your action for Dirac was a function of psi and psi star. So your two independent variables was the state and its complex conjugate. And this psi evolve in time. So that means we are in what we call the Schrodinger picture. In the Schrodinger picture, if you remember Quantum Mechanics 101, the Schrodinger picture is where the time evolution is put on the state, while the observables, the operators you use to observe something, are fixed in time. They are not moving in time. There is another picture, which is called the Heisenberg picture, where the states are constant. So you just have the initial state, but the time evolution is put on the observables. We often stick to this one, but this Heisenberg picture can be interesting. In quantum field theory, very often we have a mixture of both. We have what we call the interaction picture, if you have that. So for some, anyway, so it's not the point. So you have different pictures you can play with. So, sorry? This one is for Schrodinger, yeah. So that's Schrodinger picture. Now, you have Balian and Veneroni, we'll just call them BV, had the idea to actually build a variational principle which mixes both the Schrodinger and the Heisenberg picture. So what they did was to, instead of having psi and psi star as your variational quantities, they have the state described by a density matrix. So that's the exact density matrix, not just the one-body density matrix like we did before, which you can write for a pure state, something like that. So that's the state of your system. It evolved in time, according to the Schrodinger picture. And they also allow the observable to evolve in time, according to the Heisenberg picture. And they built an action-like quantity, from which they can get Schrodinger using a variational principle, so using stationarity of the action. Now the reason I'm doing that is because we will get TDHF. I mean, I'm not going to do the derivation, but I will just show you how we get TDHF in which variational space. Because now we have two variational spaces to play with, one for the state and one for the observable. And that will tell you what you are allowed to do and what you are not allowed to do with TDHF. Oh, you're always allowed to do whatever you want. It's just, is it going to be optimized or not for what you want to do? At some point, we should invest in some white chalk, Enrico. The left. The rectangle, okay. Where? Ah, this thing. Okay. I mean, white on white, I'm sorry, but I'm not colorblind, but still. We cut the recording. Anyway, so the variational, the action now is a function of D and A. And it's written like that. So you have the time integral from the initial time to the final time, as usual. There is a term before that. There's a term which we need of A at the time t1, D at the time t1. minus the time integral t0 t1 dt trace of a of t I d on dt of d of t, and probably plus commutator of h and d of t. Let me check if it's correct. It's not correct. I is there. Okay, so this term doesn't concern us very much, but it does. We need it for when we do the variation with respect to d. So what you want is to do the variation of s according to the variable, to the observable a, and you want this to be 0, and you also want the variation of s according to the variation of d to be 0. Now, like we did in the Dirac case, we had to impose that there was no variation at the initial state and the final state. Okay? Here, so that's what we call boundary conditions. The boundary conditions, which, how do we treat the variation at the initial and final states? Here, what we need as boundary conditions is that we assume we know what is the state at the initial time. So that's our boundary condition. So I can't allow any variation of d at the initial time. And I want to observe something at the final time. So I fix what is the observable at the final time. So the variational principle I'm building here is optimized, will be optimized for only one thing: the expectation value of an observable, of a given observable at the final time t1, knowing the initial state. So it means that I can't, in principle, I can't use it for anything else. Like I'm building, you know, an equation of motion. I'm building a theory which is optimized only for one thing: to calculate the expectation value of one observable at one time. If I change the time, if I do that for another time, I might end up with a different set of equations. If I change the observable, I might end up with a different set of equations as well. So it's only optimized for one thing I want to do at one time. Okay? So when you try to look at the variation according to A, when you don't restrict the variational spaces, so if the first term is 0, because A at time t1 is fixed, it's my boundary condition. So that's going to give 0. And then the variation according to A, you see, this term here doesn't depend on A. So it's only going to affect this one. So what I have is just integral t0 t1 trace of delta A of A and I should have this one. So now that I can allow any variation of A. It's an arbitrary variation. I can. So this should be 0 for any variation of A. For this to be true, the only possibility is for what's here to be equal to 0. All right? That's the only possibility, because this should be 0 for any variation of A, so the only possibility is to have this to be 0. And if you look at it, what it is just Notice that I took h bar equal 1 in my in this notation. Is d on dt of d, and I can put the I here, and then I get equal to h commutator of h and d. Now what is this equation? It's the exact equation for D, and it's actually the Schrodinger equation in the Liouville form. So it's exactly equivalent to Schrodinger. I can write the Schrodinger equation in this form relatively straightforwardly. So it's fine. Why did I do that? To show, as I told you, when you have a variational principle, if you don't do any limitation of the variational space, you should end up to the exact case. The exact case here is Schrodinger. Now, if you do the same thing with respect to the variation of D, what you end up with, I mean, it's a bit more complicated because you have to do some integration by part. But at the end of the day, what you will get is a similar equation, but instead of D, you have A of T. That's the Schrodinger equation, but in the Heisenberg picture. Okay, so you see that you get both pictures, the Schrodinger picture and the Heisenberg picture. So now you know that your variational principle is exact if you don't do any approximation. Well, you can start doing approximations. So I don't have time to do the derivation on the board. It's done in the notes. But you can trust me, if you restrict the variational space for the state D to independent particles, so your D of T is just phi, where phi are Slaters. So that's the variational space for D, and now you also have the variational space for the observable. And if you restrict this variational space to one-body observables, so one-body observables, these operators you can write like in first quantization a simple sum of operators acting on each particle. In second quantization, it will just be an operator with matrix elements times A dagger A. So that's a one-body operator. Now, if you restrict your observable space to be one-body operators, what do you get? You get the TDHF equation. So the reason I'm doing that is to show you that in principle TDHF is only optimized for expectation value of one-body observables. Everything which is outside of this space for observables, you can do the calculation. You have your Slater, you can do the calculation, but you don't know necessarily if it's going to work. Because the theory is not optimized for that. Okay? So in principle, if you want to be safe, if you want to be on safe ground, you should only use the theory for what it is optimized for. In this case, that means TDHF can only calculate expectation value of one-body observables. And you may remember at some point I told you that if you do a deep inelastic collision, so if you collide two nuclei violently, you end up with many fragments. So you end up with a distribution of fragments with a distribution of masses and charges. So for instance, if you look at the mass of the fragment you form after a deep inelastic collision, blank, what you end up experimentally will be something maybe like that, quite broad. And what you will calculate with TDHF will be something much narrower. And that's one of the reasons why people stopped doing TDHF in the early 80s. They were interested in going to intermediate energy heavy ion collisions. They were building accelerators like Ganil or stuff like that, which were made for this sort of deep inelastic collisions. And they realized, and they were interested not only in the average, but the average was okay. TDHF will predict what the average is, but not the width. So they said, okay, TDHF is crap. They stopped using it. But later on, with the work of Balian and Veneroni, they realized that it's just because TDHF is not optimized for this quantity. I'll show you why it's not, the width here is not one-body operator. So A is just the number of particles. So the number of particles is a one-body operator. Okay, it's just counting the number of particles, that's a one-body operator. But if you want to have the width here, what you need to have is the standard deviation of n. So that's square root of the expectation value of n squared minus the expectation value of n squared. So this is the expectation value of a one-body operator. That's good. You can do that. But now, when you do that, the expectation value of a square of a one-body operator, you will have elements like that. Part of it will be written as expectation value of A dagger, AA. That's outside the one-body space. And that's why TDHF didn't reproduce this width here. So what do you do in this case? We say, okay, I have a theory which doesn't work for what I want to predict. And you have a variational theory like that. What will you do? Sorry? And you could do it, but yeah, you could eventually do that. That would be with, that's how you do to get the pairing. Pairing will help, but not enough. Yeah. No, that was quantity of that form. But that you have many quantities which can be put in that form. Pairing will help, but not enough. If you put pairing, you will have something like that, say, but still not wide enough. Again, for instance, if you were to, you can derive TDHFB, time-dependent Hartree-Fock-Bogoliubov, from the Balian-Veneroni variational principle. And what you will do here is still to have one-body operators to get TDHFB. So you will have a wider space here, because instead of independent particles, you will have independent quasi-particles. Okay? But you still will not touch the one-body operator part. So that's why I tell you, I mean, looking at a theory from a different derivation is sometimes very enlightening. So even if you are including pairing with BCS or with Bogoliubov, you get a theory which is only optimized to one-body operators. So you will still have this problem of the width. So what shall I do? Clearly, it's not going to help to change the variational space for the state. So I can try another variational space for the observable. Okay, so in particular, I could have anything larger which will incorporate squares of one-body operators. Okay? Now the problem is getting TDHF from Balian-Veneroni, it's 1 or 2 pages. It's not so bad. But then it's become very, very complicated when you try to go to something else than one-body operators. So they managed to do it, but it's about, I didn't put it in the notes because it's about 20 pages derivation, and it uses stuff from quantum field theory, Grassmann algebra, all that sort of thing, which is a bit of a nightmare. But essentially what they did was to use a variational space which is an exponential of one body. And the reason, and they were interested in this quantity, but I will show you that this is actually giving what you look for. It's relatively, I mean, I will not showing you, but just writing it. So the so if you define your operator A as exponential of minus, I'm not sure you need the minus, but it doesn't matter. Epsilon f, where f is a one-body operator. Now at the final time at t1, you compute the expectation value of this A. That's what your theory is optimized for. And so you will have an expectation value of that. And if you do it for small epsilon, okay, you can do a Taylor expansion. What you will find is, I'm not sure there is a minus, I should check. Yes, there is. So minus expectation epsilon expectation value of f. So that's the first, that's a Taylor expansion of that. Sorry, I forgot to say it takes the logarithm of that. Takes the logarithm of the expectation value you want to calculate. First order in epsilon is just the average. That's what TDHF is made for. But then you will have another term which will be epsilon squared f squared minus f average squared. That's just my standard deviation squared. So that's the fluctuations, the variance of the operator f. So it's a, and then you have higher order in epsilon. So I'm not telling you what are the equations you need to solve. No, it's not really the point. I'm just telling you that by changing your variational space, you can optimize for what you actually want. And it's actually working then when you do Bagnan-Veneroni with this variational space. So what you end up with is a theory which is called time-dependent RPA. Remember RPA, what we did was looking at small fluctuations around a minimum of energy. Now what we are doing, because we have small epsilon here, we are in TDRPA, you are looking at small fluctuations of the action, because it's a variational principle on the action, small fluctuation of the action around the stationary path. That's why it's called RPA, and it's time dependent because it's on the action, not on the energy. Okay? So, yeah, should stop here. I can show you one figure, because otherwise it's just formalism and you don't know what it's made for. Magic number z equal 50. Now you can use this TDRPA to calculate what will be the distribution of the number of particles in the fragments. Well, there are a lot of things you can't do with TDRPA, but I'm just, for this system you can do it. And what's interesting is, okay, well, what you will get for the symmetric mode where the shell effects are present, you will get a much narrower distribution than for the other modes. You see the distribution is much wider when you don't have shell effects than when you have shell effects. So I mean, that's something we know from experiment. We know that if we look at fermium-258, we have a symmetric peak which is very narrow, and we know it's because of shade effect, or at least we expect. But this is confirmed by calculation with this theory. So just to show you one example of application. So you can do that for fission, or you can do that for deep inelastic and so on. Alrighty. So I'll stop here, and we will have a tutorial this afternoon. This afternoon we will, if you, we can still play with the code, and you can still look at what I gave you yesterday. If I have some time, for those who don't want to do the simulations or could not make it work on their computer, I'll try to write some exercise sheet where it's on pen and paper should be okay. Technology is good enough for that. Okay, thank you very much.